Hello and welcome to our talk, Geometric Methods in Computer Vision. I'm Ian Klein, joined by Jose Agudelo, Brooke Dippold, and Alex Kokot. Here's our contact information. So one concept that's very important to computer vision is the idea of congruence. We want to be able to match two objects that we think should be in the same class. And so a natural question arises, like what makes objects congruent? If you look here at the triangles below, you may think that the two on the left are congruent and the one on the right isn't, but why is that the case? If you only allow for translations, maybe the two on the left aren't congruent. And this sort of gets into one way to define congruence, which is that of transformation groups. If you can transform two objects onto each other, then they're considered congruent. Two specific transformation groups that we're looking at are the special Euclidean group, which is composed of translations and rotations, and the equiaffine group, which is composed of translations and all area preserving linear transformations. So in particular, these triangles at the bottom, the left two are congruent under both groups, but assuming they all have the same area, all three triangles are congruent under the equiaffine group. A concept that goes hand in hand with congruence is that of invariance. These are properties of curves which do not change under transformation. These are important because if two curves are congruent, then they will have the same value for their invariance. Two particular invariants that we're going to be looking at are Euclidean curvature, which is denoted kappa, and equiaffine curvature, which is denoted mu. Another property that's key with transformation groups is invariance. And we have here two moving frames, the Euclidean and equiaffine moving frame. They both have invariant properties, which is why they're so useful in like tracking sort of the motion and curvature of a particular curve. The Euclidean moving frame consists of a unit tangent vector and a unit normal vector. And these are always perpendicular to each other at the same length. Whereas the equiaffine frame consists of two vectors that have a constant magnitude of their cross product of 1. Right, so you also want to be able to reconstruct curves from this invariant of curvature. And this is pretty easy to do with Euclidean curvature. If you're given an arc length parameterization of Euclidean curvature, these formulas exist to reconstruct the curve.
Reconstructing curves from their equiaffine curvature is slightly more difficult. It is known that when u of alpha or curvature is constant, you can solve exactly, and the curvature is a hyperbola. When the curve is 0, your curve is a hyperbola. When the curvature is less than 0, your curve is an ellipse, and when the curvature is equal to 0, you get a parabola. We specifically looked at solving for when curvature is analytic using power series, and when curvature is smooth but non-analytic using Picard iterations. Here are some examples of reconstruction using power series. The method is described within our poster, but here you can see the ellipse and hyperbola-like behavior for each of the curves generated here.
Right, so the chief method we used for doing this for non-analytic curvatures was to use the Picard iteration methods to specifically approximate a tangent vector t of the curve with a given curvature mu alpha. And the way this works is that we set up these two iterative equations right here for the tangent and the normal vector, and we take their limit as n goes to infinity and integrate the result. We can then get a parameterization for our curve, gamma. Here, this t naught and n naught just simply define the orientation of the reconstruction. So when we take the mu alpha is equal to -1, just like Brooke has showed us, we get an ellipse. Here, the t naught and the n naught have initial conditions 1, 0, 0, 1, and the Picard iterations approximate to a circle in the following way. Here we have a non-analytic function on the left and its reconstructed curve on the right. The non-analytic function here on the left comes from the bump function seen on the poster.
One natural question reconstruction is how stable are our reconstructions under small perturbations? Say we're taking our curvatures from a data set and we use separate approximation methods to reconstruct our curves. How confident can we be that the curve we get at the end of the day will be pretty similar to what was originally there? The answer our group found is that under some lenient circumstances, There's a definitive yes to this problem. Yes, we can be sure that our curve will only slightly be altered if we slightly alter our curvature. As shown here, when we take just a sine function as our curvature and then reconstruct it, and then we look at several perturbations of it by bump functions, we see that the resulting curves on a fixed interval will be more or less the same. However, this is a result with some nuance. When we look at the global behavior of these curves, and we take several intervals of our sine functions and perturb sine functions, we see much different behavior. Some of them can even be closed curves, even taking just these small deviations from our curvature.
That concludes our presentation. We would like to thank our mentors, Irina Kogan and Eric Geiger. This REU project was supported by the NCSU Department of Mathematics and the NSA REU grant listed right here. And thank you to our PIs, Matt Olofsson and Seth Sullivan.